Recording pro. Okay, welcome everyone to our seminar. It is my pleasure to introduce Jelena, who is doing her PhD at Charles University under supervision of Martin Balko. And she will tell us very exciting generalization of Erdős-Szekeres theorem. Please.
Thank you, Maria, for the introduction. Yes, so let's talk a little bit about an Erdős-Szekeres theorem for point sets, which will somehow be restricted, and this you will find out soon how they will be restricted. But first, I want just all of us to be on the same page, so I will talk a little bit about the Erdős-Szekeres theorem and its history, just to make sure everybody knows what we're talking about. So the setup will always be a point set in the plane. And I will always assume that my point sets are in general position, meaning that I do not have 3 points on the same line. And the Erdős-Szekeres number will be the minimum number n, such that any point set of this size has little n points in convex position. So whenever I have this many points, I must have n points in convex position. So this is a number that Erdős-Szekeres came up with all the way in 1935. And let's see what we know about this number. So first I will just give you a little example of what is the number ES4. So first I will show you that it's at least 4, at least 5. It's larger than 4 because there is a point set of 4 points which does not have 4 points in convex position. And it is exactly 5 because however my point set of 5 points looks like, I can always find 4 in convex position. In particular, if my convex hull is at least size 4, I already have them. And if I have a triangle, then the 2 points inside will form a convex foreground with another side of the triangle, with one of the sides of the triangle. And in general, what do we know? Well, the number for 3 is 3 because 3 points in general position are triangle. For 4, it's 5. For 5, it is 9. Here are 8 points that don't have a convex 5-gon. If you want, you can try to find one, but you can also believe me. For 6, the number is 17. Here are 16 points that don't have a convex hexagon. And this is all the exact numbers that we know, but you can see some pattern there. And actually, Erdős and Szekeres in the 60s, they proved a lower bound for the number, which is exactly the pattern you see above, right? So that's the best lower bound that we have. And the best upper bound is this one. So I will not explain the lower bound, the upper bound to you, but it was a recent breakthrough by Suk, later improved on a little bit by the other authors. And in particular, we know that the number is exponential, right? And the conjecture is that the exact value is the one that Erdős and Szekeres suspected, but we don't know for sure. So I won't focus on this, but that is the conjecture, okay? But what does Erdős-Szekeres theorem tells us? It tells us whenever I have some points at P of n points, then I have log n points in convex position. And what I want to talk about now is, what if I don't look at any possible point set? What if my point set is somehow restricted? Then what happens for convex point sets? Can I have larger than logarithmic size? Can I have some polynomial size? And I will also mention what happens in higher dimensions as well. Okay, so let's see how I'm restricting the point sets. So I want to define some sort of measure of restriction, and I will call this measure the diameter of my point set. It will be the ratio of the maximum and minimum distance between 2 different points in my point set. So just to give an example, these point sets are not in general position, but they give you an intuition of what the diameter could be. So if I have a grid, square root n by square root n grid, then the minimum distance is 1. Let's say I can always assume that the minimum distance in any point set is 1. I can always just scale up, right? So the minimum distance here is 1, and the maximum is just the largest diagonal, which is square root times square root of n. So here in particular, the diameter is of square root n order. And if I have, for example, just n points on a line, the diameter there will be order of n. And in fact, this is exactly the range that diameter can have. And one observation is, sorry, I misspelled diameter. But the diameter delta of my point set is always at least square root of n. Why is this? It's a sort of a geometric packing argument. So if I have a point set, let's assume minimum distance is 1, then I can draw little balls of or circles of radius 1/2 around each of the points. The total area of this is n times pi/4, because each circle has area pi/4. And then I know that the diameter must be at least square root of n, because the circles are actually, the circle is the object that minimizes the diameter of this area, right? So this is fact known from before, right? And in fact, it is known exactly like what is the constant here. So in particular, there is some constant alpha 0, I'll call it. It's this number here. And whenever I have alpha larger than this fixed constant, I can find a point. There is some point set that has diameter exactly alpha square root of n. And for anything that's smaller than alpha 0, then there are no examples of such point sets. And just for some notation, I will call the point sets which have this diameter of order square root of n dense point sets. So these are the densest. This is the densest a point set can be, if it has the smallest possible diameter. And now I want to explore how this relates to the Erdős-Szekeres theorem. So what can I say about convex subsets of my points? So first, I will show you a result of Pavel Valtr from the 90s. This was part of his PhD thesis, and he showed it doesn't look so nice, but the statement basically tells us if we have a dense point set, meaning that my diameter is square root of n, then I do actually indeed have a polynomial-sized subset in convex position, where the polynomial is some beta times n over 1 over n to the power 1 over 3, where beta is a constant depending only on alpha. So this is the main result that I will talk about this. I will talk about at this talk because it's the simplest one to show the proof of. But you might want to what happens if the point set is not dense, but the diameter is somehow larger. So already Pavel asked this, and he managed to show that if I have diameter up to n to 3/4, there is still a polynomial-sized point set. You can see that he showed it to up to 3/4, but still there is the diameter can be up to n, so there is something to improve there. And another way to generalize this is to go into higher dimensions. And recently, Bukh and Dong, they showed that if I have a dense point set, and now dense meaning that it is the dth root of n, where d is the dimension I'm working in, I have, again, a polynomial subset, polynomially-sized subset in convex position. So these are the two ways you can generalize Pavel's result. You can generalize it to any diameter and also generalize it to any dimension. So that is what we want to do. And that is exactly what we managed to do. So the results I want to tell you about, so this is Pavel's generalization, and we actually managed to extend this interval all the way to 1, not including 1, because actually the constructions of Erdős, which show the lower bound for the Erdős-Szekeres theorem, they can be obtained with diameter n. So there is no hope if my diameter is exactly n, but up to n, I want to show something better. And we did exactly this. And in addition to extending it all the way to the in the diameter, we also extended it in the dimension, meaning that for any diameter and any dimension up to 1, so this is the range that the diameter can be, in dimension D, I can find a polynomially sized subset in convex position. Now, the proof is not pretty. It's a lot of calculations. So I will show you the proof of Pavel's original paper and briefly explain what is the idea, what we do, because, let me repeat, it is just not pretty. But Pavel's proof is a fun one, I think. It's a probabilistic argument, and the idea is neat. So let's try to go through it. So once again, we have a point set which is dense, meaning that the diameter is alpha squared of the band for some alpha. So let's show that we have this many points in convex position. The idea will be, I want to place some circle which will contain my point set, and on this circle I will place some unit area rectangles which are tangent to my circle, and I want to place them in such a way that whenever I can find at least one point from my point set in each of these rectangles, they form a convex K1, where K will be the number of convex points I'm looking for. Yes, so that is the goal. That is the simple idea. But what we want to show is that actually there is such a placement. So this is where the probabilistic argument will come. We want to show that there is at least some constant probability that for some placement we have such points. Okay, so slowly we will get to that, but first I need two main lemmas which will help me prove this fun thing. So the first, I call it the minor lemma because it's not really important, but I just wanted to have a picture. So the first lemma, it just tells me that if I look at my point set and fix some point, the number of points from my point set at some fixed, which are at some distance j, there is some limited number of points from my point set that will be at this distance. So this is again some sort of packing argument, right? I want to divide the plane in such a way that if I have 2 points in the same region, then this is not possible. The minimum distance will no longer be 1. And one way to do that is this pretty picture, let's say, is to use 15 j lines through this point P, which is fixed, and some circle. The circle will have radius j plus 1. And you can see that if I have 2 points which are in the same region and they're the same distance, then you can do some calculations. You can look at them, but I don't want to go through them, and see that then the distance between these 2 points will be strictly smaller than 1. So this is just a lemma we will use. Just remember that for any fixed distance, we have at most 60 j points this distance. Yes?
So it's written integer, so that part integer is crucial. It says integer distance j.
Yes.
It's really crucial that it's integer, or?
Yes, it will be at distance. Okay, so it should be at distance, kind of at the ceiling of my distance should be j. So I will kind of divide my points at some point into layers, and in each layer I will know that it is at most 60 j. If that makes sense. So yes, just keep the lemma in mind. But now I want to go to the actual probabilistic argument. And the key lemma, which looks not so pretty, but the main idea is that I have my point set, right? Points, whatever they look like, and they're contained in some circle of radius depending on my alpha, right? So roughly alpha square root of n. And I want to take a random rectangle. So all my rectangles, they will look like this, where this side will have some s, length s, and this one will be 1 over s. And they will be centered at some point. And they will form some angle with the x-axis. So this one is maybe not great, but so this direction forms some angle phi with my x-axis. So this is how you can characterize a rectangle. So the randomness will come from picking some, I will pick some random point inside this disk, Q. Let's say it's here. And I will pick some random angle phi. Well, let's say it's this one. Then my rectangle will look something, this is not very parallel, but it will look something like this, right? So by picking a point and the direction, I am exactly defining some rectangle, and I want to see what is the probability that inside such a random rectangle, I have at least 1 point from my point set. Okay? And this I will use later for prove the main theorem. So how do I do this? Let's see. So instead of this rectangle, should I have one point? I will, instead of this rectangle, I will consider a slightly smaller rectangle, which is to depend on some parameter delta, and just its smaller side will be smaller by delta. And I want to see what is the probability that I have exactly 1 point inside this smaller rectangle. And this will, of course, be a lower bound for the probability that I have at least 1 in this random bigger rectangle. So how do we show that how do we show what is the probability that we have exactly 1 point in this smaller rectangle? So first, what is the probability that I have a point A, some point A is inside my random rectangle, yeah. So it should be, what is the area of the rectangle? It's 1 over delta, right? And my point needs to be in the intersection of this rectangle and my disk, and the disk has radius roughly n, right? Because my not radius, sorry, area, because the radius is roughly square root of n, and this I can use to approximate the probability that I have 1 point. Then, what is the probability that I have 2 points? That 2 fixed points which are different are inside this random rectangle. And once again, I need to have 1 point, let's say this one, inside. This comes from that. And then I need my other point to be also inside the rectangle, which means that it needs to lie in the intersection of this circle, which is centered at point A and has radius this distance between the points. And you can see that it's really a small angle where this point can possibly lie. So it could only lie here. And this is how we get this number. Yes, so it's not on this picture, but the probability that we have some 2 different fixed points is at most this, meaning that if I fix some point A, the probability that I contain A and at least 1 more point now is where my minor lemma comes in. is I can sum over all the possible distances where the other point would be. That's where the 60j comes from. That's how many points I have at most, times the probability that both of them are inside my rectangle, which is this one. And this is exactly this value, big O of 1 over delta squared n. So then the probability that I have exactly 1 point is at least the probability that I have at least 1 minus the probability that I have at least 2. And there is, you will have to trust me about this, but there is there is some delta between 0 and 1 for which this holds. And therefore, there is some constant such that I have exactly 1 point in the rectangle R with exactly constant probability. And if I go back, the rectangle R was this orange one, and it's a subset of the rectangle from the statement of the lemma. And therefore, this constant will also be a lower bound for the probability that this bigger rectangle contains at least 1 point from my point set. Yes. So that is how this lemma works. And now that I have the lemma, I can prove the theorem. So I will place the center C of my circle randomly, and I place my rectangles of unit area at some random angle. Just rotate them at some random angle, and the probability that I have some point in one of these rectangles, it's definitely at least as much as the probability that I have 1 point in some random rectangle, which is some constant C by the lemma, meaning that the expected number of points, which will be, of rectangles, which will be non-empty, will be at least some n over at least this number, right? Which is the number of the rectangles that I have fixed. Good. So this is how Pavel's proof works. Does it make sense, roughly?
So where did this circle of n came? I mean,
it's this is the number of rectangles that I'm using. So this is exactly the number of rectangles I can place in such.
Yeah. Okay. And why is this? I mean, why not n half? I mean, I understand that it's something you're gonna break.
Yeah, one of the calculations breaks.
Okay.
This is like Pavel did these calculations, and this is as many rectangles.
So okay, we are not supposed to see immediately.
Yeah. It's not immediately obvious. But yes.
So the placements of the rectangles are like around the circle in some previous way where the angle is random. Right?
Yes.
So in particular, the rectangles are featured.
Yes, they're disjoint and they're placed in such a way that I can always separate each of them with a line from all of them in order to guarantee that they're in convex position.
Maybe do you also know what is the size of the rectangle?
Yes. So I wrote it in the previous slide. The size is exactly this.
Okay.
So the lemma is proven for any S basically, and this is the S that I fix as the side of the rectangle. Yes. So this is roughly how Pavel's proof works. And now we wanted to somehow generalize this to extend the interval of the diameter for which it works. So we wanted to use basically the same proof, but parameterize everything. Parameterize the size of the rectangles, parameterize their area, the diameter, whatever we can, in order to see if we can in any way generalize this proof. And what we did, so the idea is we came up with some notion of regularity. And I will not define it exactly because, once again, the expressions are not very pretty. But the idea is, if my set contains a large dense subset, meaning that it has a small diameter, and the diameter is something that I can work with, knowing from Pavel's result, meaning from Pavel's result, then I'm done. That means that the other case is that my set is somehow regular. It means that every sufficiently large subset is not dense. It has large diameter. And now I will use this instead of this little minor lemma, which I used to split it into levels. So the sums in the probability will be ugly, but they will be using exactly this regularity. And now, if you limit the notion of the density with this, you can get something new, which works for now density up to 7/8. And now I do the same thing. Now I redefine what is my regularity and use the now result that I have for up to 7/8. And now I get something which works out to 15/16. And eventually this will work up to 1. So you can see why I didn't write any of the expressions, because this is a bit of a messy process, but the idea is iterate as much as you can this result which you already have, and hope something good happens, which it does. Yes, so this is our idea. It's very nice. It is currently being written. But yeah, it was very fun seeing that this actually works in the exact same way as Pavel worked, just with more tedious calculation. Yes, and so that is the idea how to extend it for any diameter. And now I want to mention what is the idea to extend it to even higher dimensions, and you'll never guess. It's used the same idea, but now in higher dimensions. So like I won't have rectangles anymore. I will be using some hypercylinders actually, which will be placed on some big d-dimensional sphere. And the calculations get even more ugly, right? But we get some nice pictures, right? So yeah, it will look something like this. I will have these spheres and these little cylinders placed on them, which will be very flat. And again, everything will be parameterized. So there will be some parameter for the area of this, and there's a lot of playing with the volumes and the probability. But once again, the pictures are nice. That's the best I can offer for extending it to higher dimensions. But yes, I kind of talked too fast this time. So yes, the main result is this one, that for any dimension and any density, we actually have at least some convex, some polynomial sized subset in convex position, where the expression for this, I can write some of them, but if you really want me to, but you will not be happy with how they look like. But yeah, so these are all the results that I wanted to tell you about. And I'm going to tell you about some other things that we want to focus on next. So we want to also tackle the upper bound, right? This is always a lower bound. This I have at least this many points in convex position, but what about upper bounds? So in Pavel's paper, he did have some random dense point sets, which could not have convex sized subsets larger than n to 1/3. And this is one of them. So this is some sort of a grid where you take every other square and pick a random point inside of it. So this is a random dense point set. It's dense because it's a grid. I already told you about the density of the grids. And it can be shown, not so prettily, but it can be shown that this construction does not have larger convex subsets. And there are also similar constructions which work in higher dimensions, but only for dense point sets. So what we would like to do is to come up with some sort of construction which will work for also larger diameters. For now, we don't have much, but this is a direction that is sort of promising. Yes, and the other thing is to generalize any other properties of point sets to any diameter and any dimension. So pick your favorite thing about point sets. For example, I don't know, crossing family, largest crossing family. What happens when the point set is dense? Well, Pavel already looked at that because his thesis was about dense point sets, but he only looked at it when they're dense. So the question is what happens if they're a bit less dense? And yeah, you can give me any problem you like on point sets, and I would like to look at what it looks like for dense, and then ideally also not so dense point sets, and maybe even in higher dimensions. Yes, so the talk was a bit shorter than I expected. Sorry if I talked really fast, but thank you.
Thank you, Jelena. Are there any questions?
Yes.
So much.
Okay, so what is the dependence of epsilon on tau? In your theorem, how does epsilon depend on T and T and tau?
Yes.
I suppose it will be something very small. What is it like?
Yeah, it's something really small, and at some point we also introduce like another parameter, which depends on tau. So let's say if I have some tau larger than 1/2, then I will have some gamma between 1/2 and 1. Then epsilon will be something like 1 minus 2 tau over 1 plus gamma. And this gamma will be something measuring my regularity, how regular I am. It will tell me how big are the subsets that, if they're dense, they help me. Right?
So this gamma is something that you can compute, like
yes. So So it will be like something like what is my regularity? Is that every?
So that's I mean that's surprisingly big. I expected something.
Yeah.
Maybe less one.
Is it? Well, gamma will be something also quite big. Let's see. I don't know exactly. but it will be something like tau minus 1. So
Yeah, okay.
yeah, those are the numbers, if I calculated them correctly. Other question?
So those three-dimensional cylinders, is this something that already appeared in this Bukh and Dong, or it is your notion that it's the...
It's similar, but I would say it's a simplification of their proof. They used some more complicated three-dimensional bodies. Yeah.
Yeah, it's
Any other question?
Maybe just a comment. So this definitely cannot be extended to tau equals to 1, right? Because
Yes, exactly.
on the line,
Yes.
you have just 2 points.
Yeah, we're not considering lines because the point set is in general position, but it cannot be extended because these Erdős-Szekeres constructions, which give the lower bound for Erdős-Szekeres, which have only logarithmic convex subsets, they can be drawn to have the diameter exactly, and so for them I cannot use this. Make sense?
So the constructions for R2 also hold you for R2 the D, I guess. It's the same.
Sorry?
Because those constructions are for the plane, right?
The
But it's-
constructions for the upper bound.
The lower- uh-huh.
There are also constructions for higher dimensions, but we're looking for like also any diameter. What we want, because Bukh and Dong also have upper bound constructions in higher dimensions.
Any more questions? So if not, thank you, Jelena, again.
Thank you.